We are asked here, we are given here that a dwelling requires 5 times 10 to the 5 kilojoules per day of heat to maintain its temperature at 22. So we expect here really that more or less we are on countries that experiencing winter, that the outside temp in their house is 10, but they want to keep their house at 22. And they want to feel warm, and then that's why they need to install an electric heat pump, which is needed to supply this amount of heat. Determine the minimum theoretical work input for 1 day of operation in terms of kilojoule. Now, to really further give a picture of the problem, let me post the sketch for this. Okay, so we have here the dwelling or your home, which is you want to maintain at 22, but the surrounding is at 10, quite cold. You don't want to have that, to feel that, so install this heat pump, which supplies this QH. In this case, QH, which you supply is just 5 times 10. Okay, 5 times 10 to the 5 kilojoules per day, meaning and every day you need to supply that amount of heat. Okay, where do you get this heat? Well, you operate a heat pump, which essentially um, works with like it's like a refrigeration system, but the only difference is that in this case your cold part is the surrounding, and you won't like to heat this up. So this is the exhaust of the refrigeration, no, meaning the heat being transferred to the dwelling or to the house. So in this case, okay, wait, let me draw the heat pump. Okay, let me sketch here how does the heat pump really looks like. Okay, so more or less these are the this is the sketch of or schematics of a heat pump. Essentially, these are heat exchanger. Okay, hex a heat exchanger, and also another heat exchanger. So this what really happens. In this case, you supply here work. Okay, you supply work through here, a shaft work or the cycle work. You supply this work so that this compressor will work and be able to compress the. If you compress the fluid, it will increase its temp. Okay, maging high temp siya, and therefore it can eject or it can release that temperature to your house, which is maintained at 22. Okay, meaning it can release that temperature to that heat. It will then term this as QH. So that because this after the compression process, the working fluid or the refrigerant used in this case will now have a high temp. So by virtue of temperature difference, heat can now flow from your heat exchanger here through your house. Okay, and then as the heat flow, then more or less it will be what will happen is that it will be wait it will be throttled here because this is a high pressure. Okay, high pressure, high temp. It will be throttled here. The purpose is to reduce the pressure at the same time to what? To to cool this to cool this down. So it will then be when you reduce the pressure, the temperature of your refrigerant will drop, and the temperature, since mas mababa yung temperature dito kaysa sa 10, heat will flow from the surrounding through the heat exchanger here. Okay, it will absorb what we call this heat QC. It will flow into your heat pump QC, and then the 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 working fluid now will have another energy that it will then be compressed again, and then the cycle continues. Okay, so this is now of low pressure. So it also follows that your fluid here has lower temperature than 10. So the heat will flow from the surrounding here, which is at 10, to the fluid there. Okay, so essentially this is the heat pump. Reversing that cycle, you'll then have a I think you'll have a refrigerator. So in this case, we already know what is QH, right? It's 5 times 10 to the 5 kilojoules. Now, the only problem is how do we compute for the minimum shaft work? What is the minimum amount, theoretically, amount of work that you need to supply to your fluid or to your compressor to effect this process, okay? And in this case, we are assuming the most efficient heat pump. In that case, we have that, we call that the Carnot heat pump. Okay, Carnot heat pump. And in terms of heat pump, we have what we call our COP, coefficient of performance. In that case, we simply define COP as what you get out of what you input. You are getting what? In this case, you are supposed to get QH out of what you invest in your system. You put in work. Okay, this is what you mean by that. And taking a balance, taking a look at this, if we do energy balance on this one, what is entering here is shaft work. Another here we have QC. I think you'll agree that what leaves is only QH. So by doing an energy balance, you'll see that shaft work is simply equal to QH minus QC. Okay, that's why we could write that QH over QH minus QC. And if we divide everything by QH, what will then the left will be 1 over QH will just be QH divided by QH will be 1, and then we'll have here QC over QH. Okay, and this is amazing here because after you obtain this one, if you are assuming that your heat pump is the most ideal heat pump that you can have the Carnot heat pump. This COP could just be replaced by this equation 1 minus QC over QH will then just be equal to TC over TH, where TC corresponds to temperature of the cold reservoir, in this case the surrounding, and TH will be the temperature of the hot reservoir, your house or your home, your dwelling. And in this case, what is COP? So COP will simply 1 over 1. 1 minus TC. What's the temperature of the cold reservoir? In terms of Kelvin, always use in terms of Kelvin. That's 283. Okay. And what is that of the higher temperature reservoir? That's 22 or 295 Kelvin. Always use Kelvin. Therefore, COP in this case will just be 283 divided 295. 1 minus that. 1 divided by that. It gives you a COP of 24.58. Wow, quite a high COP. Over there, so you assume that this is the performance of your heat pump, 24.58, which is just equivalent to QH over work shaft, or the amount of work that you need to add to your compressor here, which drives your heat pump. And to answer the question, what's really being asked is determine the minimum theoretical work input. How much work do you need to supply? Well, in that case, from this equation, really, work shaft will then just be equal to QH over COP, right? Therefore, the work that you need to supply is just equal to QH over the COP of your heat pump. In that case, QH is 5 times 10 to the 5 kilojoule, and then per day, of course, per day, and then your COP is 24.58, and that gives you need to supply, so that's 5 exponent 5 divided by 24.58. You need to supply that amount. That's, how do I convert that? Times another 1000 divided by 1 exponent 6. So roughly with the magnitude of 20.34 megawatts, okay, or megajoule, no, not megawatts, megajoule per day. Meaning you need to supply this amount of heat. No, not amount of heat, but you need to supply this amount of work in a day, 20.34 megajoules. Okay? Okay, so this is your answer. Or if you'll say that, well, the house is, this system works in a 24-hour basis, then you can able to calculate really what is the power of your, what is the power of the compressor that you need to have. You can just have it at 20.34 times 10 to the 6 joules in a day, which you assume it's 24 hours. That's 24 hours in a day, and you know that 3600 seconds are there in 1 hour. You'll be able to get, wait, exponent 6, 20.34 exponent 6 divide 24 divide 3600. You'll be able to get 235.4. This is joules per second, or the compressor must be point must be rated at 2.235 kilowatts, the most ideal compressor, or more or less, you need just to have a half horsepower perhaps. Compressor will do the job. Okay, so meaning if that house is maintained at that temp and the surrounding is also the same for the whole day 10, then more or less you need this power rating of the compressor. But the problem really is being answered already. Thank you.